Pennsylvania backcountry, 1779. While every settler rushed to slap chimneys against exterior walls before winter, Jacob Stoltz was still laying stone in late October. His neighbors called it wasteful. They called him a fool. He built his chimney stack completely inside his cabin footprint, a massive 4 by 6 foot stone core that devoured 24 square feet of precious living space. Everyone else finished their exterior stacks in 3 days. Jacob spent 8 days on masonry alone, keeping every inch of thermal mass inside the cabin envelope instead of bleeding heat to the outdoors. Then the hard winter arrived, one of the coldest on record. 28 storms, temperatures plunging to 16 below in nearby settlements. Exterior chimneys turned into heat sinks, chilling flue gases and weakening drafts. Neighbors fed their fires constantly, 6 cords of wood through the brutal months, hauling armload after armload through dangerous cold. But Jacob's interior stack? It soaked heat like a sponge, then radiated it back for hours after flames died. His cabin stayed warm enough to work without gloves while his wife Martha tallied the proof. 3 cords total, exactly half. What did this German settler understand about thermal mass and heat placement that frontier convention completely missed? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. Night wind cuts through the valley like a blade, carrying the bite of early winter across the Pennsylvania backcountry. In one cabin, frost feathers the inside of the logs despite a roaring fire that devours split oak and hickory with desperate hunger. The flames leap and dance, filling the room with light and the illusion of warmth, yet 20 minutes after the last log catches, the air goes hollow cold. Heat races up the chimney and vanishes into the darkness above, feeding the sky instead of the people who cut, hauled, and split every piece of that precious fuel. In another cabin, barely a quarter-mile through the timber, the fire burns smaller, but the room holds its warmth like cupped hands protecting a candle flame. The difference lives in the stone itself. Press a palm against the masonry and feel the truth that separates survival from suffering. Jacob Stoltz learned this lesson in the old country, where continental builders understood that a chimney could be more than a smoke pipe. In the settlements of southeastern Pennsylvania, where German-speaking families carried traditions from the Rhineland and Palatinate, houses grew around massive central stacks that served as the beating heart of domestic life. The Küche and Stube, kitchen and warm room, drew their heat from masonry cores that stored the fire's energy in tons of stone and brick, releasing it slowly through the long hours when flames died to coals and coals faded to ash. This was not innovation born from desperation, but wisdom tested across centuries of hard winters and scarce fuel. The Pennsylvania German tradition demanded that chimney stacks remain fully inside the house envelope, protected from wind and weather by the same walls that sheltered the family. Where English colonists often built their stacks against exterior walls or at gable ends for convenience, continental practice centered the entire domestic plan around interior masonry that could heat multiple rooms from a single firebox. The technique required more stone, more labor, and more careful planning, but it transformed the chimney from a necessary evil into a thermal battery that could carry a household through the deepest cold on half the wood their neighbors burned. Jacob brought this knowledge west when he claimed his 160 acres along Beaver Creek, where the valley floor offered good timber and a reliable water source, but little protection from the winds that swept down from the ridges. His first task was not clearing fields or building fences, but gathering stone from the creek bed and outcropping ledges, sorting each piece by size and hardness, according to principles his father had taught him in Lancaster County. The foundation stones needed broad faces and solid weight to carry the stack's burden. The firebox required dense, heat-resistant rock that would not crack under repeated heating and cooling. The flue stones demanded smooth surfaces that would let smoke rise cleanly without creating snags for soot and creosote. While his neighbors raced to complete their cabins before the first hard frost, Jacob worked with methodical precision that drew mockery from men who measured progress in speed rather than durability. Ephraim Baines, whose own cabin boasted an exterior chimney completed in 3 days of hasty stonework, called Jacob's approach wasteful and foolish. The interior stack would steal 24 precious square feet from a cabin that measured only 16 by 18 feet in total. Why? Sacrifice living space for a vanity project when a perfectly adequate chimney could be built against the outside wall in a fraction of the time. The ridicule came with frontier directness that left no room for misunderstanding. They called his design a stone hog that devoured materials better used for other purposes. They said he was stealing floor space from his own family, forcing them to crowd around a monument to stubbornness when they could have enjoyed the full width of their cabin. Winter was coming, they warned, and this was no time for continental fussiness when American practicality demanded speed and efficiency. The Baines chimney might not be pretty, but it drew smoke and provided heat with less fuss and fewer delays. Jacob listened to the criticism without argument, understanding that frontier communities often viewed any deviation from established practice as dangerous pride that could endanger the entire settlement. But he also knew the difference between thermal mass and thermal waste, between heat storage and heat loss. An exterior chimney surrendered its stored energy to outside air through every square foot of masonry exposed to wind and weather. When brutal cold arrived, that same chimney became a heat sink that chilled flue gases and weakened the draft needed to keep fires burning cleanly. The stone that should have warmed the house instead cooled it, creating a system that demanded constant feeding but delivered diminishing returns. The interior stack followed different principles entirely. Every ton of masonry remained inside the insulated envelope of the cabin, protected from exterior temperature swings that could drain its stored heat. The stack warmed slowly during the day as fires burned for cooking and comfort, soaking energy deep into its mass like a massive stone sponge. Then, long after the flames died and the family settled for sleep, that stored heat radiated back into the living space at a steady rate that could keep the cabin comfortable through the coldest nights without requiring constant attention to the fire. The system worked not by burning more fuel, but by using that fuel more completely, capturing energy that would otherwise escape through an exterior stack and putting it to work where families needed it most. This was the knowledge that separated old world building wisdom from new world shortcuts, the understanding that would prove itself when winter tested every decision made during the brief construction season. Jacob continued his careful work as October advanced toward November, laying each stone with the patience of a man who knew that haste in autumn meant suffering in January. Jacob began with the foundation, digging through topsoil and leaf mold until he reached firm ground that could bear the weight of 2 to 3 tons of masonry without settling or shifting through freeze-thaw cycles. The trench extended 6 feet by 8 feet, larger than the chimney base itself, to provide a stable platform that would distribute the load across undisturbed earth. He laid the foundation stones with their broadest faces down, fitting them together like puzzle pieces, and filling the gaps with smaller stones and clay mortar mixed with lime when he could obtain it from traveling merchants. Each course rose level and square, checked with a plumb line and water level borrowed from the settlement's most experienced carpenter. The firebox took shape slowly, its walls rising with methodical precision that contrasted sharply with the hasty stonework his neighbors employed for their exterior stacks. Jacob selected the hardest, most heat-resistant stones for the areas that would face direct flame, rejecting any rock that showed cracks or signs of weakness that might worsen under repeated thermal stress. The firebox opening measured 30 inches wide by 24 inches tall, sized according to principles his father had taught him, large enough for cooking and heating, but not so large that it would pull excessive amounts of warm room air up the chimney through wasteful draft. The depth remained deliberately shallow at 20 inches, forcing hot gases to radiate more heat into the room before escaping up the flue. Above the firebox, Jacob constructed the throat and damper area with particular care, understanding that this transition zone would determine how effectively the system drew smoke while minimizing heat loss. He shaped the interior surfaces to create smooth airflow without sharp edges or projections that could create turbulence or snag points for soot accumulation. The flue itself rose square and true, its interior walls kept as smooth as possible, using the best stones he could find and pointing the joints with careful attention to creating a continuous surface that would encourage steady draft. While Jacob worked through these careful details, His neighbors completed their exterior chimneys with remarkable speed but questionable craftsmanship. Ephraim Baines slapped together his gable-end stack in 3 days, using whatever stones came to hand, and mortar mixed too thin for lasting strength. The Hendricks family finished their exterior chimney even faster, building directly against their cabin's side wall with minimal foundation and gaps between stones that would admit wind and weather. Thomas McKee bragged that his chimney took only 2 days from start to finish, though careful observers noted that half the mortar had already cracked before the first fire was lit. These shortcuts reflected frontier pragmatism taken too far, prioritizing immediate completion over long-term performance. The exterior stacks certainly drew smoke and provided heat, but they also created thermal bridges that conducted precious warmth directly to outside air through every square foot of masonry exposed to wind and weather. When deep cold arrived, these same chimneys would become heat sinks that chilled the flue gases and weakened the natural draft needed for clean burning. The builders saved time in autumn, but would pay the price in increased fuel consumption and reduced comfort throughout the winter months. Jacob's approach demanded more labor, but delivered exponentially better performance through sound engineering principles. By keeping the entire chimney stack inside the cabin envelope, he ensured that every British thermal unit absorbed by the masonry would eventually radiate back into the living space rather than escaping to warm the Pennsylvania wilderness. The stack would function as a massive thermal battery, charging during the day when fires burned for cooking and comfort, then discharging stored heat through the long hours when flames died to coals and coals faded to ash. The construction sequence followed continental building logic that treated the chimney as the structural spine around which the entire cabin would be organized. Jacob completed the stack first, rising full height above the eventual roofline, then framed the log walls around this masonry core. The approach required careful planning to maintain proper clearances between combustible materials and hot surfaces, but it created a unified system where every component supported the others. The logs provided insulation that helped the chimney retain its stored heat, while the chimney provided a thermal anchor that moderated temperature swings throughout the interior space. Hans Keller, an elder from the German settlement near Lancaster, visited during the construction and approved of Jacob's methods with the satisfaction of a man seeing old knowledge applied correctly in new circumstances. Keller had built dozens of continental-style houses during his 40 years in Pennsylvania, and he understood the principles that made central chimney systems superior to exterior alternatives. He showed Jacob how to set the clearances properly, maintaining 16 inches between the hot masonry and any wooden structural members, and how to pack the gaps with clay and sand that would provide fireproof insulation without creating thermal bridges. The work consumed 8 full days from foundation to completion, compared to the 3 days his neighbors required for their exterior stacks. This represented additional labor that could have been spent on other essential tasks, clearing fields, splitting rails for fencing, or hunting game before winter reduced the available supply. Critics like Ephraim Baines pointed to this time cost as evidence of Jacob's impractical stubbornness, arguing that frontier survival demanded efficiency over perfection. Why spend extra days on masonry refinements when adequate heating could be achieved with conventional methods that freed time for other necessary work? But Jacob understood that winter would test every shortcut and reveal the true cost of hasty construction. Wood represented more than fuel in frontier economics. It was daylight, calories, and physical risk converted into thermal energy through backbreaking labor. Every cord required dozens of trees to be felled, limbed, bucked, split, and stacked in conditions that grew more dangerous as temperatures dropped and storms increased. Men died cutting firewood, victims of falling trees, slipping axes, and exposure to cold that could kill in minutes rather than hours. A heating system that used fuel efficiently was not a luxury, but a survival tool that could mean the difference between adequate warmth and deadly cold when the hardest weather arrived. The winter of 1779 to 1780 descended on the Pennsylvania backcountry with a ferocity that would earn its place in frontier memory as the hard winter. The first storm struck in late November, dumping 18 inches of snow in a single night and dropping temperatures to levels that froze spit before it hit the ground. This was merely the opening assault of what meteorologists would later document as one of the most severe winter seasons in colonial American history, featuring 28 major storms and sustained cold that shattered previous records for duration and intensity. By December, the temperature in nearby settlements plummeted to 16 degrees below zero, a reading that represented deadly conditions for anyone caught unprepared or inadequately sheltered. The cold was not the sharp, dry cold of mountain regions, but the bone-deep, moisture-laden cold of the mid-Atlantic that seemed to penetrate every layer of clothing and every gap in construction with relentless determination. Ice formed on the inside walls of poorly heated cabins, creating a crystalline coating that grew thicker each night as human breath and cooking vapors froze against the logs. The crisis attacked houses as methodically as it attacked their inhabitants, exploiting every weakness in construction and every shortcut in design. Exterior chimneys became massive heat sinks, their masonry chilled by wind and weather until the stone absorbed more heat than it radiated. Cold flue gases moved sluggishly through these chilled passages, creating weak drafts that filled rooms with smoke and forced families to crack doors and windows for ventilation even in the depths of winter. The very structures meant to provide warmth became energy vampires that drained heat from interior spaces and fed it to the indifferent sky. Ephraim Baines discovered this bitter truth during the third week of December when his hastily built exterior stack began working against him rather than for him. The chimney's gable-end position exposed 3 full faces of masonry to wind and weather, creating a thermal bridge that conducted heat directly from his firebox to the outside air. His large open hearth, designed to throw maximum heat into the room, instead created a powerful draft that pulled warm air from every corner of the cabin and sent it rushing up the flue. He could build a fire hot enough to scorch his face while his back remained cold, and within minutes of the flames dying down, the room temperature plummeted toward the freezing point. The Hendricks family faced similar struggles with their sidewall chimney, which had developed significant cracks in the mortar during the first hard freeze. Cold air leaked through these gaps, chilling the flue gases and creating downdrafts that pushed smoke back into their cabin during certain wind conditions. They spent entire days with their door propped open despite sub-zero temperatures, choosing between suffocation and freezing while precious heat escaped through every opening. Their children developed persistent coughs from the smoke exposure, and their food supplies dwindled as cooking became nearly impossible during periods of poor draft. Thomas McKee's 2-day chimney proved even more problematic, with mortar joints that had never properly cured failing completely under thermal stress. Stones worked loose and fell into the firebox, partially blocking the flue and creating dangerous conditions that threatened to burn down the cabin or poison the family with carbon monoxide. McKee spent precious hours during the coldest weather attempting repairs with numb fingers and inadequate materials, work that should have been done properly during the construction season but now demanded attention when every moment outdoors risked frostbite or worse. These failures created a vicious cycle of increased fuel consumption and decreased comfort that pushed frontier families toward the edge of survival. Wood became the most precious commodity in the settlement, more valuable than gold or silver, because it represented the difference between life and death. Men ventured into the forest despite dangerous conditions, felling trees in snow that reached their waists and hauling logs through drifts that could swallow a horse and rider. Every armload of split wood represented calories burned, sweat frozen on clothing, and exposure to temperatures that could kill in minutes rather than hours. The exterior chimney cabins demanded constant feeding, consuming 6 cords of seasoned hardwood through the brutal months as their owners fought a losing battle against thermal inefficiency. Families burned oak and hickory as fast as they could cut it, yet their homes remained barely habitable spaces where water froze in buckets overnight and children slept 3 to a bed under every available blanket. The men grew gaunt from the endless labor of woodcutting, their hands split and bleeding from axe work in conditions that turned steel brittle and made every swing a potential disaster. Jacob's cabin told a different story entirely. His interior chimney stack absorbed heat throughout each day as fires burned for cooking and basic comfort, the massive thermal mass storing energy in its 2 to 3 tons of stone and mortar. When evening came and the family banked the coals for the night, that stored heat began radiating back into the living space at a steady rate that maintained comfortable temperatures through the dark hours. The cabin remained warm enough for normal activities. Martha could tend to sewing and cooking tasks without thick gloves, and the children slept comfortably under reasonable bedding rather than every scrap of cloth in the house. The difference became measurable in ways that transcended comfort and entered the realm of survival economics. While his neighbors fed their fires constantly and still shivered through the nights, Jacob's household maintained steady warmth on a fraction of the fuel. His wife Martha kept careful count of every armload brought from the woodshed, tallying consumption with the precision of a merchant tracking inventory. The numbers told a story that would reshape building practices throughout the settlement when word spread of Jacob's remarkable fuel efficiency. During the worst stretch of January, when temperatures remained below zero for 12 consecutive days, Jacob's neighbors visited with increasing frequency, ostensibly for social calls but actually seeking refuge from their own inadequately heated cabins. They lingered near his warm masonry, pressing palms against stone that remained hot to the touch hours after the last log had been added to the fire, experiencing firsthand the difference between heat storage and heat waste. The proof arrived in measurable increments that could not be dismissed as luck or exaggeration. Martha Stoltz maintained her wood tally with the precision of a merchant tracking precious inventory, recording every armload carried from the woodshed and noting the duration of each fire's useful heat. Her counts revealed a pattern that defied frontier convention and challenged everything the settlement thought it knew about heating efficiency. Where the Baines household burned through an armload of split oak every hour during the coldest periods, Jacob's cabin consumed the same amount over 2 hours while maintaining superior comfort levels throughout the living space. The overnight test provided the most dramatic contrast between the two heating systems. In cabins heated by exterior chimneys, families woke each morning to cold ashes and stone-cold masonry that had surrendered its stored heat to the outside air during the dark hours. Rekindling fires required starting from scratch with kindling and careful coaxing, a process that consumed precious time and materials while the family shivered in temperatures barely above freezing. The exterior stacks had become thermal drains that worked against their intended purpose, absorbing heat during the day only to radiate it uselessly into the winter night. Jacob's interior chimney presented an entirely different morning scenario. The massive stone core retained enough stored heat to keep usable coals alive through even the longest winter nights, glowing embers that could be coaxed back to flame with minimal effort and fuel. More importantly, the masonry itself remained warm to the touch, continuing to radiate heat at a steady rate that prevented the cabin's interior temperature from dropping to dangerous levels. Family members could dress and begin their daily tasks without the desperate urgency that characterized mornings in poorly heated homes, where every moment delayed meant further heat loss and greater discomfort. Storm days provided an even more severe test of heating system efficiency, when travel became impossible, and families found themselves trapped indoors with whatever fuel supplies they had managed to accumulate before the weather turned deadly. During a 5-day blizzard in late January, when wind-driven snow made venturing to the woodshed a life-threatening proposition, the thermal storage capabilities of Jacob's interior chimney became the difference between survival and catastrophe. The heated masonry provided buffer time measured in hours rather than minutes, releasing stored energy at a controlled rate that stretched limited fuel supplies far beyond what exterior chimney systems could achieve. Ephraim Baines faced the opposite situation during that same storm, watching helplessly as his cabin's temperature plummeted despite burning every stick of seasoned wood within reach. His exterior chimney demanded constant feeding but provided diminishing returns, the cold masonry actually working against him by conducting heat away from his living space. By the 4th day, with no access to additional fuel and interior temperatures approaching freezing, Baines made the desperate decision to burn furniture and interior trim, sacrificing the cabin's finish work to maintain minimal heating that still left his family huddled under every available blanket. The illness test revealed another critical advantage of efficient heating systems during frontier winters, when medical care remained primitive and recovery depended heavily on maintaining body temperature and strength. When young Samuel Hendricks developed a fever during the worst cold spell of the season, his family's smoke-filled, inadequately heated cabin became a threat to his survival rather than a place of healing. The combination of poor air quality from their malfunctioning chimney and temperatures that rarely rose above 40 degrees inside created conditions that weakened rather than supported recovery. Jacob's cabin served as an informal infirmary during that period, its consistent warmth and clean air providing the stable environment needed for healing. The interior chimney's steady heat output meant that sick family members could rest comfortably without the energy-draining effects of constant shivering, while the properly functioning flue ensured clean air quality that did not aggravate respiratory conditions. When families lacked the physical strength to cut and haul additional firewood due to illness or injury, the fuel efficiency of the interior stack provided a crucial survival margin that could mean the difference between recovery and death. The mechanism behind these dramatic differences lay in fundamental principles of thermodynamics that frontier builders rarely understood but could observe in their daily fuel consumption and comfort levels. Thermal mass positioned inside the insulated envelope of a building captured and stored heat energy that would otherwise escape to the outdoors, creating a battery-like effect that evened out temperature swings and reduced fuel requirements. The interior chimney's protected location prevented wind and weather from stripping away stored heat, while its central position allowed it to radiate energy in all directions within the living space. Draft stability provided another crucial advantage that became apparent during periods of extreme cold and high winds. Exterior chimneys, chilled by outside temperatures and buffeted by wind, often developed erratic drafts that could reverse direction or fail entirely when conditions turned severe. These draft problems created dangerous situations where smoke backed up into living spaces, forcing families to choose between suffocation and freezing while precious heat escaped through open doors and windows. Interior stacks, protected from temperature extremes and wind effects, maintained steady upward drafts that ensured proper combustion and smoke removal even during the worst weather. The mathematics of fuel consumption told a story that spread through the settlement with the authority of hard numbers rather than theoretical claims. Martha's careful tallies showed that Jacob's household consumed 3 cords of seasoned hardwood during the hardest stretch of winter, compared to the 6 cords burned by families with exterior chimney systems. This 50% reduction in fuel requirements translated to weeks of saved labor, fewer trees felled in dangerous conditions, fewer loads hauled through deep snow, fewer hours spent with axes and splitting mauls when every swing risked injury and numbed hands. The daily carry distance avoided represented another measurable advantage that frontier families could appreciate in terms of reduced risk and preserved energy. Each cord of wood represented dozens of trips between forest and cabin, distances of 200 to 400 yards that accumulated into miles of walking through snow that could reach waist-deep during major storms. Having the required fuel load meant having this exposure to frostbite, falls, and exhaustion that claimed lives with increasing frequency as winter deepened and conditions worsened. Heat retention measurements provided the final proof of the interior chimney's superior performance. While exterior masonry cooled to ambient temperature within hours of fires dying down, Jacob's interior stack remained warm to the touch 6 to 10 hours after the last log was added, continuing to radiate useful heat through the thermal lag that characterized massive stone construction. This extended heat output meant that families could bank coals in the evening, with confidence that morning would bring warmth rather than the desperate scramble to rekindle dead fires that characterized life in conventionally heated cabins. The transformation began not with fanfare but with quiet questions that sounded like surrender disguised as curiosity. Ephraim Baines, who had led the mockery of Jacob's wasteful stone hog just months earlier, appeared at the Stoltz cabin during the first warm day of February with the demeanor of a man reconsidering fundamental assumptions. His inquiry carried none of the bluster that had characterized his earlier criticism, instead focusing on practical details that revealed a builder's growing respect for proven methods. How wide had Jacob set the foundation base to carry such massive weight without settling? What proportion of lime to clay had he used in the mortar to achieve joints that remained tight through repeated freeze-thaw cycles? How far back had he kept the log work from the hot masonry to prevent charring while maintaining structural integrity. These were not the questions of a skeptic seeking ammunition for further ridicule, but those of a craftsman acknowledging superior technique and seeking to understand its principles. Baines examined the interior stack with the careful attention of a man planning his own reconstruction, noting the smooth flue surfaces that encouraged steady draft and the thermal mass positioning that maximized heat storage within the cabin envelope. He pressed his palm against masonry that remained warm 12 hours after the last log had burned to coals, feeling the difference between heat storage and heat waste with the immediacy that only direct experience could provide. Thomas McKee followed within days, his own questions focusing on the construction sequence that had seemed so foolishly slow during the building season, but now appeared prescient in its thoroughness. How had Jacob managed the clearances around such a massive interior structure without compromising? The cabin's frame. What tools and techniques had he used to achieve the precise stonework that showed no gaps or weak joints even after months of thermal stress? How long had the mortar required to cure properly before the first fires could be lit without cracking the joints through rapid temperature changes? The inquiries multiplied as word spread through the settlement that Jacob's heating system had achieved documented fuel savings of 50% while maintaining superior comfort throughout the brutal winter. Caleb Rourke, whose hastily built exterior chimney had consumed enormous quantities of wood while barely keeping his family above freezing, began planning a complete reconstruction that would relocate his stack to the cabin's interior. The younger settler approached Jacob with the humility of a student seeking instruction from a master craftsman, asking for specific dimensions, material requirements, and construction techniques that could transform his energy-wasting cabin into an efficient heating system. Jacob responded to these requests with the generosity of a man who understood that frontier survival depended on shared knowledge rather than jealously guarded secrets. He demonstrated the proper technique for laying foundation stones that would bear heavy loads without settling, showed how to mix mortar that would remain strong through repeated thermal cycling, and explained the principles of thermal mass positioning that made interior stacks superior to exterior alternatives. His teaching carried none of the superiority that might have been expected from someone whose methods had been proven correct through harsh testing, instead focusing on practical techniques that others could apply to their own construction projects. Martha Stoltz played a crucial role in this knowledge transfer by sharing her detailed fuel consumption records with other women in the settlement who managed household logistics and resource planning. Her carefully maintained tallies provided hard numbers that transformed theoretical discussions into practical mathematics. 3 cords versus 6 cords, 2 hours of warmth versus 1 hour, morning coals versus cold ashes. These measurements carried particular authority because they came from lived experience rather than speculation, documented proof that heating efficiency could be achieved through better construction rather than simply burning more wood. The adoption process gained momentum through the spring and summer building season as families applied lessons learned during the hard winter to new construction and major renovations. Caleb Rourke rebuilt his chimney according to Jacob's specifications, relocating the stack to the cabin's interior and increasing the thermal mass to capture and store heat more effectively. The McKee family demolished their failed exterior chimney entirely and constructed a new interior stack using proper materials and techniques that ensured long-term performance. Even Ephraim Baines, despite his initial resistance to admitting error, quietly modified his heating system to incorporate some of the thermal mass principles that had proven so effective. The technical knowledge that Jacob had brought from continental building traditions found new expression in frontier applications that adapted Old World principles to New World conditions. The central chimney concept, developed over centuries of European building experience, proved remarkably well suited to American frontier conditions where fuel efficiency could mean the difference between survival and death during severe winters. The technique spread beyond the immediate settlement as traveling craftsmen and new arrivals carried the knowledge to other regions where similar conditions demanded efficient heating solutions. Hans Keller, the elder who had approved Jacob's construction methods, served as an informal teacher and advisor to families attempting their own interior chimney projects. His decades of experience with continental building traditions provided the technical foundation needed to adapt these principles to local materials and conditions, ensuring that knowledge transfer occurred with the precision needed for successful implementation. Keller emphasized the importance of proper foundation work, thermal mass positioning, and flue construction that would maintain efficiency through repeated use and seasonal cycling. The formal validation of these frontier innovations came nearly 2 decades later when Count Rumford published his influential designs for improved fireplaces and heating systems in 1796. Benjamin Thompson's scientific approach to combustion efficiency and heat transfer provided theoretical explanations for what practical builders like Jacob had already proven through direct application and measurable results. Rumford's work gave official credibility to fuel-saving techniques that had emerged from necessity and been validated through harsh experience rather than laboratory testing. The legacy of Jacob's interior chimney design extended far beyond individual fuel savings to influence building practices throughout regions where efficient heating remained essential for survival. The technique became part of the accumulated wisdom that experienced builders passed to apprentices and newcomers, practical knowledge that complemented formal training with hard-won understanding of what worked under extreme conditions. Central chimney construction evolved from continental tradition through frontier application to become an accepted method for maximizing heating efficiency while minimizing fuel consumption and construction complexity. The final lesson that emerged from Jacob's vindication spoke to broader principles of building design and resource management that transcended specific techniques or regional applications. If your heat source touches the outdoors, you pay to warm the outdoors. This simple truth, proven through one brutal winter and 3 cords of carefully counted firewood, became the foundation for heating system design that prioritized efficiency over convenience and long-term performance over short-term savings.